you remember last time when I touched on the issue of supernova astrozoology, I described the variety of classes of supernova explosions. Today, we'll pay more attention to one of the most important classes, type 1a supernovae. And the reason why they're so important is because they have been used as standard candles. They have been used to help us measure vast distances in the universe, the edges of the observable universe, thereby allowing us to constrain the properties of and the geometry of the universe itself, and maybe say something about its ultimate fate in the future. So this is a very important class of supernova explosion, a very special one that people here at the University of Chicago, the Department of Astronomy and Astrophysics, and the FLASH Center, which I'm a member of, have done a lot of work on, using our code, the FLASH code, to understand how these explosions happen and what triggers those explosions in the first place. I'm actually going to show you some simulations that have been done with the FLASH code at the top. Pretty cool three-dimensional simulations. Before I go on, I'll briefly remind you that the lectures will be posted online in my personal website, the University of Chicago Department of Astronomy and Astrophysics. The link that I'm showing right here also exists in the back of your syllabus. So you can download the lectures in PDF format and go over yourself. So let's talk about hanging out with bad company. What can happen? You know, when you choose the wrong friends, or maybe you happen to grow around the wrong environment. Terrible things can happen occasionally. So this is what happens to type 1a supernova. But before we understand, before we get into the deep subject, I want to remind you that those are explosions of white dwarfs. Therefore, we need to understand what is a white dwarf in more detail, and why do white dwarfs under certain conditions explode. A brief reminder that the white dwarf is the compact remnant core of the low-mass star. And again, I remind you when I use the term low-mass star, I'm talking about a star that has a mass about less than 8 times the mass of the sun. And eventually, like our sun, for example, when the stars evolve, they become red giants, they pop up, eventually they set out their outer layers, and what's left is a compact, bright, dense core, which we call a white dwarf, which under regular conditions for single stars, it just cools over time. Over billions of years, it becomes a black dwarf, because it just cools peacefully in eternity. But in a lot of cases, we'll see that white dwarfs are actually the bad company in the title of my lecture. It's these guys that are really close to another star, and due to the other star transferring mass to them, they eventually explode by a violent explosion. So some basic characteristics of white dwarfs. Their mass is about the mass of the sun. Most of them could be like 50% less massive or 60% less massive. A typical white dwarf mass about 0.6 times the mass of the sun. But that's for single white dwarfs. The ones that we find in binary systems, they tend to have usually higher masses. About 1 solar mass, or 1.2 solar mass or so, we'll see. In terms of the size and the radius, it's about the size of the Earth. So you can imagine this is a pretty dense star. You take something that's about the mass of the sun, and you compress it down to a radius. It's about the size of the Earth. That means that you really pump up the density. And a characteristic, as I'm trying to outline here in this very simple equation, density for white dwarf material, it's several tons per cubic centimeter. Picture that. Take a spoon of material. If you could take a spoon of material out of the white dwarf, it would weigh about a few cars, in weight. It's impressively dense. Being so dense and compressed, that means there's huge gravity associated with white dwarfs, and they're supported by the special exotic type of pressure that I introduced you to during the first lecture, the quantum pressure. Now, a quick reminder on quantum versus normal pressure. In a normal star supported by normal pressure, if you add energy to the star, in the core of the star, the charge is going to heat up and expand. If you remove energy, it's going to contract. Now, in terms of quantum pressure, the white dwarfs, the situation is totally different. If you remove energy from a white dwarf, it will simply cool down over time. But if you add energy and you add heat, it will keep heating up until eventually it will explode as a violent type 1a supernova explosion. Well, It's worth mentioning that a lot of work on quantum pressure and white dwarfs is due to this place where we are right now. Actually, before you enter this amphitheater, you see a nice portrait of Subramanian Chandrasekhar, one of the most prominent Indian-American astrophysicists of the 20th century, who worked out the details of how white dwarfs grow to this very, very critical limit until they eventually explode. And this is the critical limit set by the quantum pressure. And it turns out it's around 1.4 solar masses. That's a magic number. And this is a number worth remembering throughout these lectures. Those are when you grow a white dwarf above this certain mass limit, an explosion is very likely to happen. So that's the maximum mass, the Chandrasekhar mass, as we call it, the Chandrasekhar limit, that a white dwarf can attain before becoming a type 1a supernova explosion. Now, I want to switch gears a little bit and just talk why are type 1a different from type 2s, which I remind you, it's just explosions of massive stars. In this case, we have a white dwarf exploding. In type 2 supernovae, if you remember from last lecture, we're talking about a really massive star forming an iron core, which eventually collapses. Well, and that is the main difference. That's the main first difference. That massive stars will first form iron in their cores and eventually collapse and explode. Well, the situation is different for white dwarfs. White dwarfs are primarily made of carbon and oxygen material. And they don't make iron while they explode. They actually make iron during the explosion. So the timing of producing this special element is different for the two types of explosion. This is what this cartoon image right here is trying to convey. Initially, you have a white dwarf, a pretty compact star, then supported by quantum pressure, primarily made by pure carbon and oxygen. Eventually, when the supernova explosion happens and when the light peaks, reaches a maximum, you eventually see inside it formed a lot of iron, but you can't see it yet because it's surrounded by this pretty dense, unburned oxygen, magnesium, silicon, carbon, and so on material. As the supernova expands, it gets more transparent. And eventually, over time, a couple of weeks after maximum light, you can start looking into the inner layers and finally see iron coming out. Now, I'll ask you a question. Do you remember from last lecture, specifically when I talked about spectroscopy, what specifically helped us understand at each different stage what kind of elements are we looking at? Does anybody want to? Yes, sir? Spectra. Exactly. So what we do when supernova takes place, we take spectra in every single time. And in the spectra, we can identify the material that's dominating the emission, the radiation that you see from the star. Turns out early on, we see those elements, oxygen, magnesium, silicon, sulfur, and so on. Especially silicon. That's pretty strong in supernova spectra. Very characteristic element. But pretty much when we see a strong silicon line in an unknown explosion spectrum, we're pretty sure it's probably a type 1a supernova. Eventually, as things expand, we start seeing iron lines in our spectra, which basically means that we're looking deep inside the newly formed iron material. And that's the main difference between the two explosions. One makes iron before the explosion, type 2s. Type 1a's make iron during the explosion. Now, let's talk a little bit more about the explosion process. Once you've made the white dwarf, once it's reaching this very critical 1.4 Chandrasekhar mass limit, what's really going on? Well, as I said before, white dwarfs are supported by quantum pressure, which tends to be very unregulated if you change it or if you tweak it a little bit. So the deeper you go in the white dwarf, the larger the pressure, the larger the quantum pressure, the higher the density, the higher the temperature. But remember, you need those conditions to counteract charge repulsion. What I've talked about before is when you try to bring two charges of the same nature together, if you try to bring two protons together, two electrons together, they tend to repel each other because of charge repulsion. Therefore, you need to add energy to those particles to bring them strong, really, really tightly together to start initiating nuclear reactions. Thereby, it's in the center of this white dwarfs, where the temperature and density is pretty high, that you have the right conditions. And once you get to this critical mass, and you start having those reactions take place, basically burning carbon and oxygen, because that's what the white hole is made of. That's a runaway process. Runaway processes are very important in physics. A familiar runaway process you're with is a nuclear explosion. It's something that the more you change the temperature, the more unregulated it becomes. It doesn't regulate itself. And then it's a runaway, nothing can stop it, it will explode. So those explosions of white dwarfs, in the end, we don't expect them to leave a remnant. They blow up the entire white dwarf. So they form a lot of iron, and all the supernova ejecta has a certain structure, but there's nothing left behind. The entire material is unbound and travels in space. No neutron star, no black hole left behind. So how that actually happens? And we have to connect the way we think it happens with what is implied by the observations. If you remember the observations that I outlined to you earlier, you start with something that initially shows intermediate mass elements like silicon, magnesium, carbon, oxygen in the spectrum. But eventually, as time goes by, you start seeing iron. So we need a type of process, specific type of explosion, that produces this chemical evolution that we observe. Now, there's two types of ways you can burn material. And when I say burn material, it's a chemical reaction. Actually, you frequently apply one of those processes when you turn on your engine in your car. It's a brief detonation. So those processes are in our daily lives and sometimes can be deadly, as I'll show you later. But the two differences, and I'm going to use some scientific nomenclature now to distinguish between them. It's a deflagration and a detonation. The difference between a deflagration and a detonation is that a deflagration is a mild burning of material without explosive outcome. It's kind of like a flame. It's a subsonic flame. Don't be scared by the term subsonic. When something is subsonic, it means that it travels with a speed less than the speed of sound. Some fighter planes from the US Air Force will break the speed of sound frequently, and that's where they become supersonic. So subsonic versus supersonic is your speed relative to the speed of sound itself. So deflagrations happen in a subsonic speed. They burn material subsonically. While detonations are explosive and they burn material supersonically. And they involve the production of shock waves, blast waves. Nuclear explosion creates a blast wave, and that's what rips the buildings apart eventually. This blast wave is basically a rapid, sudden change in pressure. If you were to look at the pressure of the material, in front of the shock wave, the pressure is what it used to be, but right at the shock wave front, it's much higher. And that sudden difference in pressure is what's driving these explosions eventually. Now, which one of the two different explosion types that we know of applies to type 1a supernova and carbon oxygen white dwarfs? Well, let's think about it. What if, can white dwarfs just purely explode via detonation? Sorry, via detonation? Well, it turns out that they can, but that's not commensurate with the observations. Because detonations proceed so quickly by this blast wave that eventually you would burn out the entire mass of the white dwarf, which was carbon and oxygen, into iron. That's not what we see. If you remember the picture I showed you earlier, during the first week of the evolution, we see intermediate mass elements. We see silicon, magnesium, carbon, oxygen. Therefore, just a pure detonation model cannot explain the spectral properties of type 1a supernova. So that's out of the picture. What about a pure deflagration? Maybe carbon oxygen white dwarfs burn slowly, eventually, carbon and oxygen until the flame reaches out to the outer layers and explodes the star. Well, that's not good enough either, because deflagration burns material so slowly that we would expect to see a lot of unburned material if that was the case. We would expect to see a lot of carbon, silicon, and oxygen, magnesium that pertains for a long time during the spectral evolution. We don't see that. So what's going on here? Well, How about trying a transition from deflagration to detonation, as we call it DDT? This is the prevailing model within the confines of gravity, of course, which is what supports the white dwarf, that we think leads to a successful white dwarf explosion that also matches the observational characteristics that we see with our telescopes. So the way we think about this picture is that initially you have a deflagration that takes place in the center of the carbon-oxygen star that slowly starts spreading material. You have a propagating flame outwards, from the center outwards, that eventually transitions to a detonation and starts expanding and blowing up the entire white dwarf. Now, this transition is important because it allows for enough iron to be made at early times, but also for enough unburnt carbon and oxygen material to be left over, to be left behind, which is what you really need to explain the spectral properties. And it also gives the right, it turns out it gives the right energy that you observe from type 1a supernova, if you consider this process. Again, it gives the right distribution of the elements, as I showed you in the cartoon image before. And it matches very, very closely a wide variety of observations, which is, after all, what we theoretical astrophysics are about. It's matching what we see through our telescope. It's not about playing with video games in our computers and toy models that make no sense. In the end of the day, it's all about matching what we see with our telescopes. And that's a picture that seems to match more closely what's going on when white dwarfs explode. Now, this is it's still a very hot research topic. And there's a lot of contribution that's been made with that by groups here at the University of Chicago, doing a lot of simulations with the flash scope. It's a problem that we come across in our social and daily lives all the time. I mean, you've heard about some deadly explosions that happened in Waco in Texas, fertilizer explosions, oil train explosions. Those are sort of like a terrestrial analog of what's going on in a white dwarf. They involve transition from a deflagration to a detonation. And only recently, thanks to the developments in algorithms and multidimensional codes like FLAS, and the availability of high-end computational resources like NIRA, the Argonne National Laboratory, we've been able to simulate in detail a white dwarf gravitationally confined that transitions from deflagration to detonation. And it turns out that it's a very, very complicated, turbulent process that's involved. The flame is not a laminar thing that just spherically, again, breaking the spherical symmetry. I'll be coming back to that all the time. It's not something that spherically propagates in the star. It's more complicated than that. And it propagates in a very complicated manner, and it's turbulent. And that itself, the turbulence of the flame, plays a role into eventually transitioning to a detonation. Very complicated physics. But then that raises the question, okay, we kind of understand now how white dwarfs explode, and in what manner they should explode to explain what we see with our telescopes, but how do they actually grow to their second critical mass in the first place? And now that's another hot research topic, and the matter of one of the most heated debates in our supernova community today. There's two competing models that attempt to explain how white dwarfs, the progenitors of type 1a supernova, how white dwarfs grow to this typical mass before they eventually explode. And I'm going to talk about both of them. The first model I'm going to be talking about, we call it in fancy terms the single degenerate model. We call it single degenerate because, well, single because it involves one white dwarf getting mass from a normal star. And we call it degenerate because white dwarf is supported by quantum pressure. It's degenerate material. So white dwarfs are all degenerate, by the way. So the first idea is that you can grow a white dwarf to the critical mass by accreting material from a companion star in a binary system. And how would that actually work? How would this mass transfer work? Well, I need to introduce you to a few terms here before I tell you how. Go back. Okay. So, when you have a binary system, you have two stars basically orbiting around each other. In general, those stars will have different masses and different sizes, different radii. And usually, you can have a more massive star and a less massive star. Now, if you remember, more massive stars evolve faster than low massive stars. They burn their nuclear material at a higher rate, and they evolve faster. So you could have a situation where a star evolves faster than the other one, and puffs up, becomes a red giant dwarf. And at this point, it starts transferring material to a white dwarf. But that process, the mass transfer process itself, is initiated when stars reach a characteristic size in their evolution, when they feel the Roche laws. Roche is the name of the astronomer that talked about this context for the first time. No need to be scared. You can imagine the Roche laws as, invisible boundaries around the star, which basically outline the region within which the star exerts gravitational pull. So it's the area of gravitational influence for its star. And the size of this area, of this Roche law, is different according to the mass of the star and the size of the orbit, how far apart the binary stellar system is. But a general rule of thumb is that more massive stars will have the bigger Roche laws. And when a massive star fills its Roche law, when material gets so packed in this boundary, the star cannot hold it together anymore. It's not gravitationally bound to the star, so it's going to start transferring material to the companion star. This is kind of like what I'm showing here. You can have initially a main sequence star, like our sun, one solar mass, and a companion that's more massive. That's still less than 8 solar masses, but more massive than this star. Well, the more massive star is going to evolve faster than the less massive star. Therefore, it's going to reach the stage of puffing up and creating a red giant before that star does. And once it gets there, look at that, it expanded in radius. So it's filled its Roche law. And that's when it starts transferring material to the other star, eventually staying without the surrounding material. So you have a white dwarf now here, left over from that star evolution. But now you still have this main sequence star. That will eventually evolve too. Over time, it will become itself a red giant, and it will start transferring material to the white dwarf eventually. And then it will start growing to the white dwarf, to this critical mass, triggering a supernova explosion. So this process of mass transfer happens via what we call an accretion disk. And an accretion disk is kind of like its own object. There's fields and fields and fields across astrophysics that try to understand how accretion disks emit radiation, how they grow, how material is actually rotating in this disk before it's reaching the central object. It's a big field of study on its own, accretion disk astrophysics. And it turns out that when the massive star reaches this Roche law and starts transferring material to the white dwarf, it's not going to happen in a kind, polite, quiescent manner. It's going to happen quite episodically, and matter is going to collide with different regions. It's going to have rotation and angular momentum, and eventually it will settle down to forming this flat disk around the object. And that's how you transfer mass eventually. That's the picture we see of transfer mass from the massive star to the white dwarf. It starts coming in and it starts circling down to the surface of the white dwarf, slowly growing its mass. This region of impact, when you first impact material from the star into the accretion disk, we call it the hot spot, because this is a region where it emits a lot of energetic radiation, X-rays, you can see through this place. And that's how we actually find a lot of binary systems like that. In many cases, we don't see them. We don't see two stars separated. with each other. It's so hard to distinguish them at large distances. So indirect evidence, amongst other, a lot of other indirect evidence for finding them, is looking at X-rays potentially emitted by stars that are accreting to white dwarfs, so-called X-ray binaries. This system is unstable because you start transferring mass to a pretty hard to regulate structure, a white dwarf. So one would think, okay, eventually you transfer all the mass there, you get 1.4 solar mass, and you have a very energetic explosion. Well, it doesn't quite happen that easy. Along the way, as you add mass to the white dwarf, there will be flashes of radiation. The white dwarf will not like it, in other words, the fact that you give it a lot of garbage, to say, don't give me that, I don't want it. It's going to start to puff it up, and these puffs, those flashes, will be energetic flashes of radiation. Those are called novae, and that's someone asked me that question last time. That's one of the main differences between supernovae and novae. First of all, it's a wildly different process, and second of all, it does not disrupt the entire star. A nova explosion or a nova flash is not going to disrupt the white dwarf. And it's going to happen repeatedly in many cases. So when we find those X-ray binaries, those cataclysmic variables, as we call them, again, another Greek word, I'm happy to report, we'll see them periodically flashing out. We'll see over time, there's a flash, and then later on, there's another flash. But the system is still there. Eventually, under the right conditions of mass transfer, that flash will turn into the explosion. When you get to the 1.4 solar mass, that's the point of no return. That's when the white dwarf is going to blow up, becoming a type 1a supernova. And now I'm going to show you a simulation that's done with a flash code here in the University of Chicago. Again, very important to emphasize on trying to do these things in 3 dimensions. Nature is 3-dimensional. It's not spherically symmetric. As you will see here, the flame, the transition from the deflagration to detonation that happens is not happening in a spherical way. Quite the contrary. This blue outline here is the edge of the white dwarf. And this really hot spot in the center is where the flame is initiated. It's the core of the white dwarf, the center of the white dwarf, where we initiate the flame. And this is how it looks like. It kind of looks like a nuclear bomb, to be honest. Like a nuclear mushroom. So the flame, now you have subsonic burning going on initially, that transitions to supersonic, right here burning, expanding out the surface of the white dwarf. And as you can see, it doesn't blow up the white dwarf symmetrically. It blows it out in the surface. It has a some extra exit point. Kind of looks like a nuclear mushroom, doesn't it? And then we rotate the simulation to just show you this 3-dimensional structure.
1.3 seconds? Is that what that is?
Sorry, what's the question?
Is the time scale there is 1.3 seconds for that to reach the surface?
Well, yes. You can see it right here. This is pretty fast. We're talking about, once it turns supersonic, it runs with several thousands of tens of thousands of kilometers per second. And this is the size of the Earth, remember. So if you do the math, you'll see it's a pretty fast process. And this is where we say the shock breaks out of the white dwarf envelope. Eventually, there's more evolution after that. This is just part of the story. And there's more evolution because that flame is going to engulf the surface of the white dwarf eventually. So it's going to propagate around the surface of the white dwarf before the entire structure becomes unstable and starts expanding outwards. So this is how we think with our simulations that white dwarfs explode. This is the insight we can get about doing this complicated physics with a supercomputer. Now, this is one theory. I told you there's 2 competing scenarios for how type 1a supernova explode. Over the last 12 years, 15 years, there's been another scenario that's been getting a lot of traction, mainly because we always had one problem with type 1a supernova, given the single degenerate scenario. The problem was that we said, hey, you just transfer mass from a companion star, the white dwarf explodes, but what happens to the companion star? Is it still there? If it's still there, why don't we see it? Well, it can be really hard to find. That's one partial answer to the question. But still, we should be able, we've seen a lot of Taiwanese supernova, some of them in relatively nearby distances. We should be able to see hints of the presence of the companion star that transferred mass to the white dwarf in the first place. And that's what this model is trying to address. When you have two white dwarfs spiraling against each other, I'm going to talk about this process, which we call the double degenerate scenario, because it involves two white dwarfs, two degenerate stars. Nothing is left behind. There's no remnant, there's no companion, the entire structure blows up. So we wouldn't expect to find remnants or companions or anything left over from this explosion. So I showed you some pictures during the first lecture of some supernova remnants like the Tycho supernovae, pretty spherical structures. And I pointed out that we've looked and looked and looked in the center of this. We couldn't find anything. We didn't find a star there yet. We haven't. And that would be consistent with that picture. Now, to honor Albert Einstein, the general theory of relativity, and having years ever since, that process has a lot of general relativity, has a lot of Einstein quality. It turns out that when you have two really, really massive, dense objects in the universe, they curve space-time. Picture this. Picture like taking a piece of paper and start placing heavy objects. I mean, paper is not probably the right material, but you will see it curving down. Eventually, when you place something really, really heavy, it's going to make a hole through the fabric of the paper. This kind of similar thing happens in real space-time. The heavier, the denser, more gravitationally strong the material is, the more it's going to curve space-time around it. This is a revolutionary idea proposed by Albert Einstein, which was the basis of the general theory of relativity that we're still using today. As a matter of fact, a lot of people ask me, okay, the general theory of relativity is great, and you can say all these things about black holes and white dwarf mergers, but what does it matter to me? You all are using general relativity in your daily lives, because I'm pretty sure most of you have used the GPS, the global positioning system. And the way GPS works is by utilizing satellites that go around the Earth to all coordinate and pinpoint your location on the surface of the Earth. Well, if you were to do this without calculating general relativity, you would get your position really wrong. It would show you like you're in Lake Michigan or something instead. The reason we get it so accurate is because we account for the curved space-time due to the gravitational field of the Earth. And we make those corrections in our GPS devices, that's in our phones, to get our location accuracy. The GPS you have in your smartphones or in your cars, they have general relativity in them. That's why they're so accurate. So it is a thing that we face in our daily lives, as a matter of fact. And it's also very important for this type 1A double degenerate scenario of white dwarf mergers. In this case, when you have two white dwarfs orbiting around each other, they create ripples in space-time. Because again, they're so dense, and they curve space-time so much. And then you have two regions of curved space-time moving around each other. It will create ripples in space-time, in a similar way that you see ripples being formed in a lake when you drop a stone into a lake. And those ripples, actually, there's multi-million-dollar projects online, like LIGO, Laser Interferometer Gravitational Observatory, that we're trying to detect those ripples of space-time. There was actually, 2 weeks ago, an announcement that stirred a lot of scientific discussion of maybe we might have found, using LIGO, the first evidence of gravitational waves, as predicted by Albert Einstein. It's really hard to detect. You have to build very, very delicate, advanced machines to be able to detect these ripples in space-time caused by things like that, by double white dwarfs or double black holes or double neutron star systems. So, but what happens? Well, when those two white dwarfs orbit around each other and produce those gravitational waves, you can imagine that energy is conserved. That's the main principle in physics, and so I agree on that. But when you start transferring energy from the binary system into the space-time by creating those ripples, that means you are removing energy from this binary system. And when you remove energy from a system that is in orbit, it coalesces. The orbit is reduced. And the objects spiral down to each other, spiral down into the abyss. And those two white dwarf mergers will eventually collide. And if the combined mass of this white dwarf material is more than this Chandrasekhar limit, 1.4, it's going to blow up. It's going to make a type 1a supernova. If it's not, if you get a 0.6 solar mass white dwarf with a 0.4 solar mass white dwarf, it's very likely it will make just a 1 solar mass white dwarf. The two objects will merge, make a bigger white dwarf. But under the right condition and given enough time, they will spiral down together and they will explode. So, and that process works in similar ways like the single degenerate process, the spiraling down. Because in reality, when you say spiraling down, what happens is that you are eventually transfer mass, white dwarf material, from the one object to the other. And again, mass transfer in binary systems involves Roche laws. So one white dwarf will eventually, as they spiral down to each other and the orbit gets smaller, will reach this limit, this gravitational limit of the Roche law, and start irregularly and uncontrollably transferring mass to the other white dwarf. And the runaway, it's a runaway process in this case, like it's a runaway process with nuclear explosions. And virtually you will have the entire white dwarf transferred to the other white dwarf, either making one larger white dwarf or exploding into a type 1a supernova explosion. So this is the picture we have now about type 1a supernovae. We know that they're very bright. We know that they have standard luminosities. And I'm going to get to that in the next couple of slides. But we're still debating what system or what systems gives rise to this spectacular explosion. We have two competing theories, the single and the double degenerate scenario. And they both have their problems, and they both have their promises. In the case of the single degenerate scenario, the main problem we still have is that we haven't found companion stars. Where are they? We should be able to find some sooner or later. There are some arguments from this army right here. This army of scientists claims, well, maybe you don't find them because those companion stars are mainly what we call M-dwarf stars. This is a special category of stars that's really dim. And they're so dim that it's really hard to find. So they're dodging their way out of it by saying, well, we don't find them because we can't find them. The other guys here, this camp, the double degenerate camp, they can explain this problem. Like, there's no remnant left, that's why we don't find it. But at the same time, a lot of people are concerned whether this process accurately reproduces the observed spectral evolution of these events. What I told you in the beginning of the lecture. At first you have carbon, oxygen, silicon, magnesium, and later on you see iron. They more or less get it, but they don't get it all correctly. So there's still problems trying to get the right spectral evolution in a double degenerate. They both have their problems. Some people try to create peace, raise the white flag and say, hey guys, maybe both of them are relevant. And then now that will be an issue of trying to understand for what kind of supernova, for what kind of type 1a supernova, one channel is more relevant than the other. So be either one of them or both of them. That's the whole idea. And there's a third parameter to that, which is the supernova rays. As I told you, with our modern technology, our modern robotic automated telescopes, we can detect thousands of type 1a supernovae in databases. A lot. We have a lot of data. We've seen a lot of type 1a supernovae. So we know what the rate of type 1a supernova is. Now, each model you're talking about here will have to match the observed rate of type 1a supernova explosions. And it's still not clear which one of the two does, because the rate is a matter of the progenitor system. And that becomes a question, what do you see more in nature? You see systems like that or systems like that? And what is more relevant to the rate you measure for type 1a? Still a very open question and a matter of heated debate. Sometimes people actually get mad at each other. I've been in conferences, I've been in meetings, and they're going to use some nasty terms to each other and get really, really personal with this. But type 1a supernovae are more than just an explosion. They're a tool that's aided cosmologists to understand the properties of the universe. This guy right here is Edwin Hubble, one of the most prominent American astronomers of the 20th century. You know, all the pictures that I've showed you come from the Hubble Space Telescope, which is named after his honor. This guy created a very important diagram in the history of cosmology, the Hubble diagram. What this diagram helped us understand by using type 1a supernovae is what the properties of the universe are in the far reaches, in the edge of the universe. Again, type 1a supernovae are very bright. They're actually about 100 times brighter than typical core collapse type 2 supernova explosions of massive stars. They're pretty bright. And they're also very standardized. If you think about what I said during this lecture, you need to reach this magical 1.4 solar mass circular limit in order to get that explosion. That means they're pretty standardized. You expect all type 1a supernova to result from white dwarfs about 1.4 solar masses. That means that they will most likely give out the same luminosity, and their light curve, the way the light evolves over time, will actually look very, very similar for type 1a supernova. Extremely similar. That means we can actually see a type 1a supernova, measure how much light we get here at the Earth, how much light we see through our detectors. We know how much light is intrinsically produced at the site of the supernova. And using this information, we can easily in astrophysics calculate distances. And this is where type 1a supernova becomes important, because the standard candles, or now they like to call them standardizable candles, because you have to do some calibration in the light curves. But eventually, if you do that, if you observe a lot of supernova explosions, a lot of type 1a supernovae, you can measure distances and make a plot of distance versus luminosity. And that can be translated into a plot of how far away things are moving depending on their distances. And that was the groundbreaking discovery by Hubble. He found out, oh crap, the further an object is, the faster it moves away from me. The Hubble law. The further an object, so you can imagine things, so the universe is expanding. That's the answer, right? He determined by just looking at type 1a supernovae that the universe is expanding, a revolutionary discovery. Kind of like the surface of the balloon. You probably heard this analogy before. Take a balloon and you put some dots on the balloon and you start blowing up. You will see each little dot is moving away from all other dots at faster rate the faster they are from each other. That's kind of the picture we like to use when we are talking about the expansion of the universe. And that discovery, later on, when we had better telescopes and better technology, we could observe type 1a supernova more accurately and at larger distances. And we'll figure out, by doing a lot of Hubble diagrams, that not only the universe is expanding, but it's accelerating, groundbreaking, revolutionary. Like when you have something that has mass and expands, you would expect at some point it either starts to decelerate or at least starts to come back together and collapse, because you just have gravity, you just have mass. Why the heck is the universe accelerating? What's going on? So it turns out that's what gave rise to the notions of dark energy and dark matter. We call it dark because we're simply so ignorant and we don't understand what it is. We still don't know what dark energy is. We're trying to figure out what dark matter is. By making Hubble plots, Hubble diagrams, we have figured out what the constituents of the universe are. And it was pretty humbling to find out that normal matter makes up only 4 or 5% of the universe. The reason the things you see right here, the Earth, the Sun, you, me, this lecture, it's just 5% of what's really out there. There's another 25, 27% of dark matter, which is matter like we can touch, but it does not interact with light. That's why we can't see it, and we call it dark. And there's several theories about what kind of particles, what kind of exotic particles, like axions, you hear some weird names coming around, make up this dark matter. And there's also a 70+% of dark energy that we'll have no idea. All we know is that it has about the same density in space-time, but that's about it. We don't know what it is. We don't know where it comes from. We have no explanation. But the fact that we found this groundbreaking discovery, we found that there has to be dark energy and dark matter to account for the rapid acceleration of the universe, led to a Nobel Prize in 2011. This gentleman right here, all of whom I've had the honor to meet personally in the past in conferences, they awarded the Nobel Prize in 2011 for that discovery. And just before I close, I like to close with pictures. Last year, 2014, we came across a very nearby type 1a supernovae. So that's supernova 2014J. This is it right here. You see, as I said in the first lecture, outside the entire galaxy. This is just a star in our galaxy. It's in the foreground. But in this galaxy right here, which is in our galactic neighborhood, I don't remember the name of it, M30 something. That's where type 1a supernova took place. Now, that one was a little bit sad because it took place right in the plane of the galaxy. So basically what you see here, you look at the galaxy edge on. Galaxies, you can either look at the face on, and you can see all the spiral arms and everything, or you can look at the edge on. Depends on what angle you look at. And it happened right in the plane of the galaxy, which means that there's a lot of material that light has to go through before it gets to our telescopes. Well, that means that there's a lot of extinction, a lot of reddening, a lot of dust that this light from type 1a, from this type 1a supernova, has to go through to get to our telescopes. So it was kind of sad because it's rare to find a type 1a supernova so close. We found one really close where we think, oh wow, we can actually try to find a progenitor maybe, or try to find a companion star because this is really close. But then we're like, damn, so much dust and so much dirt around this that we can't really, figure it out clearly. It's pretty much distinguished. But it was a pretty cool event.
How close?
That's a good question. I would say, on top of my head, several hundreds of millions of light years, which is close for us. So, to summarize what I talked about before, today we focused on one of the main types of supernova explosions, the type 1a supernovae, which are explosions of degenerate white dwarfs supported by quantum pressure. We saw that there is this characteristic critical mass limit that when a white dwarf is reached, the Chandrasekhar mass, 1.4 solar masses, they will inevitably explode by a very violent and bright supernova explosion, type 1a supernova explosion. We also talked about alternatives and how do you actually grow a white dwarf to that mass. And there's the two competing scenarios, single degenerate versus the double degenerate. In one case you have a more massive star a normal star transferring mass into the surface of the white dwarf, thereby growing its mass. In the other case, you have two white dwarfs spiraling down to each other, eventually reaching the Chandrasekhar mass, merging and exploding as a type 1a supernova. Astronomers are still trying to understand which one, or if both, are relevant to type 1a supernova. But we also dug deeper into the process of the explosion itself. We've done numerous supercomputer 3-dimensional simulations, and we came to the conclusion that the most likely scenario to understand how a white dwarf explodes and how to explain the observed spectral characteristics is via deflagration to detonation, subsonic to supersonic burning transition. And of course, the highlight about type 1a supernova is because they've been a tool for us over the last few years since Edwin Hubble outlined their importance to understand the properties of the universe itself. Because they're bright, they have standard behavior, because they all result from one white dwarf for 1.4 solar masses. And we can use them and we can see them at large distances to deduce the properties of the universe itself and say a few things about its fate and where we think it's going to go from here. And that's about it. Thank you very much.
Single degenerate scenario, how you would have a standard candle, but under the double degenerate scenario, it could be at least twice as big.
So he's asking, he's saying that it's easy to see that under a single degenerate scenario you would have a standard candle, standard behavior for the type 1a supernova, but it's harder to see for the double degenerate scenario. Well, the answer here is that both explosions are triggered and happen when you get to that critical mass, 1.4 solar masses. It doesn't matter how you get there, it's about getting there. So a white dwarf merger scenario, double Jenner scenario, under certain conditions will get two white dwarfs of smaller mass to collide into a white dwarf that's more than 1.4 solar masses and it's unstable. And that's exactly when it's going to explode. So in this sense, they are, even double degenerates are standard. There will be a little bit of, range in luminosity, but they're pretty standard.
But if you have one solar mass degenerates
Right.
colliding with each other, then you're combining two.
Right.
You're not limited to one.
You will not use up the entire material. You will not use up the entire material for the explosion. The material will explode. You will have some differences in the light curve, but they will not be as pronounced as you would expect to make a huge difference in the actual, as compared to other type 1A supernovae. So it's not, when we say standard, it's not like they all are identical, but they're so close enough within some range that within the error of measurement, we can use them to measure distances, even for type 4 double generators.
What happens to the unexploded material?
The unexploded material in the case of single degenerate or double degenerate? Either. So the unexploded material is just going to be unburned material that you're going to see it's going to be expanding in the outer layers of the supernova ejecta. And you're going to see its effects in your spectrum. You know, if you remember, I said there will still be a little bit of carbon and oxygen that's unburned from the outer layers of the white dwarf that's going to be expanding. And you will see that. It's just going to be blocking some of your light that comes from within. It's going to be absorbing some of the light that comes within. Ladies first. Yes?
How long can we see a supernova last in the sky?
Well, for type 1A supernova, the typical time scale we see it's 2 weeks. Within about a week or 10 days or so, they will reach a peak luminosity. They will grow to a peak luminosity and eventually will start fading away as they expand. So 2 weeks is a typical time scale. Yes?
Do you see the difference in the progenitor material? So because mass transfer from a red giant is getting, I would guess, hydrogen, and mass transfer from the white dwarf is carbon and oxygen coming out. Does that make a difference?
Well, not necessarily, because hydrogen is something you can burn very easily. It's a very light material, so it's going to all be mixed with white dwarf material, and it's going to be burned very, very easily.
So the main thing is just mass.
Yeah, that's the main thing that triggers. There's small differences. People still have problems with the spectra that you predict with double degenerate scenario, which goes back to what you were mentioning, and they're still trying to figure out those differences. The answer they're giving us, the theories from the double degenerate side, is that we don't yet have accurate 3D simulations to be able to produce a correct input to our spectral codes to figure out what's going on. So it's all a matter of time. You know, they're improving, so we'll see what they have to say in a few years. Yes?
Okay, when you're talking about the burning that's going on in the star,
Yeah.
is that a nuclear reaction? Or?
Yeah, we're on nuclear reactions.
Okay, and you talk about the transfer of mass from one star to another.
Right.
Now, are those molecules, ions, how does that take place? And through what distance are you talking about?
So the distance of a binary system, I mean the separation between the two stars, can range anywhere from from binaries that are really close to each other, which they're practically inseparable. The stars are almost touching each other in a sense. In this case, you can imagine a distance that's equivalent to the radius of the sun or so. But in some other cases, they're more separated. They're, the distance between the Earth and the sun, or the distance between the Jupiter and the sun. You can have larger separation distances. But really, mass transfer happens when they get closer to each other. And there's several ways that stars, over time, orbit closer to each other. And then there was another question about
The transfer of the mass, is that a stream? And are they ions?
the material, they're not molecules. Molecules cannot survive those temperatures and pressures. They will be destroyed. Molecules are very delicate. They will be destroyed very easily in these conditions. So there's pretty much ionized atoms. Matter is so hot, the gas, it's an ionized gas that really gets transferred. That even atoms themselves are not put together. Their electrons have escaped because it's so hot. So you basically have nuclei. It's a plasma. You have nuclei and electrons together. It's ionized gas. Yeah. Yes?
Are all the white dwarfs characteristically, the star ages down to iron, or what about the ones that go on and heat and form neutron stars?
So those are two different problems. So what differentiates white dwarfs from the other remnants is the mass of the initial progenitor that created them. The dividing line is around 8 solar masses. For stars that are lower mass, like our sun, they will never make neutron stars. They will never make black holes. They will make white dwarfs. Stars,
It's the iron core.
the massive stars get to the iron core only. So you have to have mass more than 8, 10, 12 solar masses to be able to eventually form an iron core. I would say more than 12, actually. Yeah?
In the double degenerate scenario, each component has its own warping of space-time. Does each component have a Roche lobe?
Yes. Roche lobes are imaginary surfaces that outline the region of gravitational influence for each star. So no matter what kind of star you are, if you're a black hole, neutron star, you can define a Roche lobe around anything with mass. Yes?
You speak of carbon, oxygen, silicon, nickel, whatever. These would be standard formats for the atoms involved. They would not exist as such in a plasma.
They will be ionized. So you will have the nuclei of these elements.
Yeah, but the absorption for a nucleus
It's going to be different lines.
is going to be different than it would be for integrated.
Right. But it's going to be the same element uses. And you know, we have calibrated in laboratories in the area what different ionized levels of material, of carbon, oxygen, silicon will produce. So if you have a silicon atom and you remove one electron,
Okay.
it's going to produce a different line than a silicon atom that remove 2 electrons.
Okay.
So that way,
So all of the possible progenitors have been marked or
yeah, we know where to find the lines exactly.
However, if you take a look at the nuclei alone, the arithmetic doesn't come out right. If all of these mechanisms involve fusion alone,
But it's not just fusion.
there's no fusion.
There is fusion, but it's not the only process. There's
Okay. So there's fusion and decay going on at
Yeah.
the same time. Thank you.
yes.
You mentioned Einstein. He didn't know of the acceleration of the expansion. Did he have any hints about it?
Well, that's a good question. Einstein, one of the most famous equations of Albert Einstein is Einstein's field equation, which basically is the equation that tries to describe the curvature of space-time around massive objects, black holes, for example. And occasionally, but you can use the same equation to just model the entire universe. It doesn't matter if it's one object or a collection of objects or the entire universe. And before he died, he added this cosmological constant, this lambda, Greek lambda, which he thought has got to be there, not for any rational reason, but he was convinced that something has to be there to balance out the expansion. And that was people call what the dark energy is basically in the equations is this cosmological parameter lambda. Before he died, he said, in his deathbed, he said, that was the biggest mistake of my life. Turns out it wasn't a mistake. So yeah, he didn't predict whether the universe is expanding or anything of the like, but he formed the basis, the formalism, the equations that eventually are used today to incorporate these observations with theory to figure out what the effect of the acceleration is and why it's 70% versus 60%. So.
The acceleration, are there astrophysicists who are dealing with that, figuring out, well, what does it mean for all their observations? And suppose Einstein had lived in the internet age, what would he have? What would we have seen?
Probably a lot of cool stuff if Einstein was alive today. But, it's a pretty much undisputed fact that comes from a variety of different observations, not just the acceleration by type 1a supernova, but we're actually able to look at the first picture of the universe using a microwaves, a cosmic microwave radiation, which is pretty much when the universe was young enough and started cooling down as it was expanding. Eventually, radiation decoupled from matter and escaped matter. And that echo of radiation, we can still find today and detect it, and we can map it across the sky. And that's a huge confirmation of this type 1a based study. Right? Just by doing that and looking at the distribution of the initial radiation, we can figure out, again, what the contribution of dark matter versus dark energy versus normal matter is as well. So this is an undisputed fact that the universe is expanding and accelerating. Nobody's debating that. And for people that are looking into objects that are really far away from us, like supernovae, or people that are trying to use the next generation of telescopes to discover the first galaxies, that were formed. Because the further you look away, the further in the past you look. They will be interested into the acceleration. It's got to be boiled in for the further away you go from the observer. It has to be boiled in.
We know about the acceleration just quick. For what, 20, 30 years since when was that determined?
The acceleration of the universe?
Right.
I would say, I would say it was about 20 years, 30 years. Yeah. People talked about it before, but there was no direct observational confirmation. The idea has been around for longer, but the observations came in. The confirmation. Yeah, 20, 30 years. Next question? Yes.
Is there any fundamental reason why we need to assume that gravitational constant is constant throughout the universe?
You're raising the idea of modified Newtonian dynamics, MOND. So we don't have evidence yet, at least, that G, the gravitational constant, changes. There's no evidence of that. People have done experiments. We've sent satellites out. I don't recall the name, but we've sent satellites out to try to do exactly that, to orbit around the sun, figure out over time, based on the influences of other celestial objects nearby, whether G is what we think it is, and it's constant. There is a very interesting theory that's been proposed as an alternative to dark energy, which is, well, maybe we just don't know gravity all that well. Maybe we know gravity in local distances. We know that it pulls things together when things are closely in space, close in space. But when for objects that are really, really far apart in space, maybe gravity behaves in a different way. Maybe it's actually repelling things. And that's the theory of modified Newtonian dynamics, MOND. So there's credible scientists, minority, but credible scientists that have proposed as an alternative to the dark energy problem that maybe we just don't understand gravity on large scales.
Would that describe the uniform behavior?
Some of it. The problem is that it won't describe all of it. And we have no reason to assume that G is changing. So far we haven't found any evidence of that.
How did Einstein use his speed of light as a fundamental universal standard? How he arrived to that number, and then what are the mechanisms that light travels only at that speed? Not only light, but things without mass.
That is a hard question you're asking me. We're still working things like that. So light, as you said, travels at a constant speed, and Einstein knew about the speed of light when he worked the theory. It's not like he discovered the speed of light.
But how did he connect it to formula?
Well, one big issue for Einstein when he was working on a special theory of relativity, which is the first part before the general theory of relativity, is the issue of causality. It's how information is transferred. What's the importance between cause and effect, and what is the maximum speed so we can communicate information with each other. Light itself, I said in the last lecture that we know it has a dual nature based on quantum mechanics. In some experiments, it behaves as a particle, so you can reflect it off a mirror and it reflect back, kind of like if you throw a ball on the wall and it reflects back. But in some other experiments, it behaves as a wave. wave particle duality. You send light through a tiny hole, from the other side you see ripples, characteristic of wave-like behavior. So the electromagnetic waves, which is what light is made of, travel to the speed of light in the vacuum, which means a material that's not, not interfering with any other dust or anything. Just in the vacuum, it's the ultimate speed, the way like neutrinos. But there's not just light. There's other particles, neutrinos specifically, that also travel at the speed of light. And they have, neutrinos are very special. In this lecture, we're focusing on optical, or on what information we get from light. But neutrinos are just so hard to detect. They have their mass, they're ghost particles, we call them. They don't interact strongly with matter. So it's really hard to build detectors that can cast those. And they also travel at the speed of light. So from a variety of experiments prior to Einstein coming into play, we were unable to find any evidence that anything can travel faster than the speed of light. And when you try to think, to conceptualize cases where something like that can happen, then weird things happen, like inversion of causality. You could, you could give that lecture before I even gave it. The hour of time is reversed if you try to imagine cases where things travel with speeds faster than the speed of light. So it is at the edge of our knowledge. People have tried to see whether, maybe the speed of light itself is not actually constant, kind of like the gravitational constant. They've done numerous experiments to try to figure whether at different frequencies light travels with slightly different speeds. Nobody has any credible evidence. It's an experimental fact at this point.
So where do I look to find out if somebody's explaining somehow what is the mechanism that light...
To produce light?
Yeah, what is the mechanism in the universe that produces light travel at that speed? What is making it go that speed? Is something that it cold the photon and then expel the photon every step of the way?
It's a combination of all these processes. So to have light travel through a medium, you first have to produce it. And to produce it, there's a variety of ways you can. One way to produce light is, for example, when you have an atom. An atom is made of a nucleus and electrons. Sometimes those electrons, one of those electrons will fall to a lower orbit close to the atom, to a lower energy state. But to conserve energy, it will emit that energy difference into a photon. This is the basis of quantum mechanics, Max Planck. This is how quantum mechanics started. And that's how one way you can produce light. There's more ways. You can just heat matter up so much that it produces its own light eventually by atomic transition. So light is produced at a finer atomic level. And then there's a question of how does this photon you produce propagates in the universe? Well, it doesn't matter whether light is propagating through vacuum or it's propagating through water. If you go at tiny scales and you try to follow those light particles as they propagate, in some cases, they will be in dense materials. So what you would see is that you have particles here, and then light just reflects off every single particle and scatters around before eventually moving into the vacuum. But the speed that light travels in between those collisions, the speed of light, pretty close. And eventually, it escapes this dense condition to vacuum and just free streams. You have a particle that just free streams in space. And it hits the outer atmosphere of the air, and then it will start doing the same thing again. Boom, 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 scatter around. Eventually, it will come down to the telescope.
Yeah, when the light is scattered, for example, on glass or something, and you have the diffraction, the light with more energy travels faster or slower?
No. So there is a correlation between the wavelength that the light transfers. So if you shine X-rays through a glass versus optical, the refraction properties are not going to be the same because they have different energy. But the speed is always going to be the same. That's the difference. The angle might not be the same, but the angle of refraction might not be the same, but the speed of light, regardless of what you're talking about, microwaves, optical, X-rays, gamma rays, it doesn't matter. It's always C. It's always 300,000.
But so the refraction, the index of refraction doesn't indicate a change in speed of the frequencies?
It's mostly a frequency change.
Okay.
We're getting throw down some equations there. Yeah.
Okay. Now, I want, let's source study the space-time of the double degeneration scenario.
I'm sorry?
Is there a source that I go to find out about the space-time of the double degenerate scenario? Is there a source out there, a book
Oh, a book?
a journal or something?
Yeah, I mean, I've recommended in this lecture a book by Craig Wheeler called Cosmic Catastrophes. I can write it down for you. And that has a lot of information there. Yeah.
What's his name?
Craig Wheeler.
C-R-I-D.
Craig. C-R-I-A-I-D. Wheeler. W-H-E-L-E-R.
Yeah. Okay. And I have one more question.
Yeah.
The black hole, the black hole. How would you describe the description of the black hole? It pulls in other mass from the high gravitation. How does that relate to these white dwarfs, black hole?
It's a different compass concept. So white dwarfs are not made by massive stars, they're made by low mass stars. While black holes are 100% of the time made by really massive stars.
Okay. No, I'm trying to shoot, but if the white dwarf comes near the black hole, what type of, is there any studies on it?
So you can have systems where you have a black hole and a white dwarf, and what's going to happen, first of all, you're going to produce gravitational radiation, which means that you will start bringing the orbit down closer, and eventually the white dwarf is just going to go into the black hole. You're going to make a bigger black hole. So if you want whatever you want with a black hole, there's always going to be a black hole. It's not like normal arithmetics. You know, it's not
It's the same phenomenon.
So yeah, so if you had a say if you had a 2 solar mass black hole and 1 solar mass white dwarf, and eventually they coalesce, then you would end up with a 3 solar mass black hole.
So it's the same accretion process.
It's the same. It's losing energy of the orbit due to the gravitational radiation, the ripples in space-time. Yeah. Anything else?
Now we want to know.
I like it. You gotta be eager. All right.
Thank you.
Thanks.